So evidence for chemical reactions. Okay, there are 4 observations that indicate a chemical reaction is taking place. Okay, I would reference these as a change in phase. Your textbook lists these as 4. I listed as 3. A change in phase. So the big ones: a gas is formed, light fizzing to heavy bubbling, or a solid is formed. Two clear solutions, when mixed, form a solid or a precipitate. You could also see a liquid form. The issue with the liquid formation is typically you can't visually by inspection see that. You'd have to monitor it some other way. Okay, but the gas and the solid formations are the big ones for chemical reactions. The other big changes would be a permanent color change. Actually, before we do that, so here we go. We've got a precipitate. How do we know it's a precipitate? We'll look at the solution. If it was clear, as in you could see through it, there was no solid blocking it. It was a liquid. The instant it now becomes opaque, if something is blocking the light passing through the sample, a solid must be present. So that's a pretty clear observation of a solid forming. Sometimes with the solid precipitate, you'll see a permanent color change. Okay, and we have to be careful here. This is not a dilution of color, but the formation of a new color. So take 2 clear liquids, mix them, oh, new color. That's a permanent color change. The last one, which is a little bit harder to actually visualize here, would be looking for an energy change. Okay, this could be seen with flames and sparks and all that, but more often than not, it's really just seen by sticking a thermometer in your reaction and noticing the temperature difference. If the reaction released heat, that is known as an exothermic reaction, and mathematically that comes down to a negative sign, okay, which is a tricky thing to watch out for, so be aware of it. Anytime negatives pop up, it tends to mess with things. If the energy change or the reaction absorbed heat, as in the temperature dropped, it is an endothermic reaction, and this is a positive energy term. The reaction absorbed energy. Okay, so let's go through those once more because I'm not sure I actually clearly stated it. A release of heat means your temperature increases, so we seem to think positive, but then realize that your energy term is negative. Okay, a bit weird, but that's the way it works. Okay. If the reaction absorbed heat, then your temperature actually decreased because it's sucking energy out of the environment. That is your endothermic reaction, and that is a positive change in energy. Okay, those positives and negatives are kind of arbitrarily stated based off of the mathematics that went into solving and determining these things. An interesting feature here is light emission considered an energy change. Is light energy? Huh, that could be a worthwhile question to ask. States of matter in equations. So looking at an equation and trying to decide what pieces of information are present. Okay, so we've got this big list of things here as an example. What things can you find in it? And I'm going to delay here for a second and then say that again. What things can you find in this equation? So we've got lots of stuff. Okay. Probably the biggest thing that's not listed neatly in your textbook is that we're looking at reactants, and these go to make products. Okay. And if we think back to Einstein's theories, we cannot create or destroy matter. Or I guess it's Newton, one of the physicists. Stop laughing at me. I don't care, let's just move on to the next thing. Arrow. Our arrow means we're doing a reaction, so we can treat that as kind of an equals. Whatever shows up on the reactant side must show up on the product side as far as the atoms go. The molecules, on the other hand, can change, but the atoms should stay constant for 95% of chemistry. Other little bits and pieces, we have plus signs, meaning that we're reacting with or also present. A big one that tends to stand out is seeing that delta symbol. That delta means change, and when it's shown over an arrow, it's really referencing a change, in temperature. Okay, and that change in temperature is externally determined, which means we are adding heat to the reaction. Okay, for cooling it down, there is no symbol for that. We would just say the reaction is cooled. Another kind of interesting symbol, Fe is iron. So if we saw an element written above the arrow, that could be considered a catalyst, at least in our Gen Chem class. Other things that might pop up, you might see Nr for no reaction. So if I realize that this reaction wasn't going to work, I'm not going to bother to draw the products. I could just write Nr, and I now know that no reaction happened. The last big thing, all of your phases end up getting included. Okay? And officially you need to be showing phase for every single species present in solution. So if you write a plus, a phase needs to appear before that. If you write a reaction arrow, a phase needs to appear before that every single time. Okay? We have mentioned it in the lab, but just in case you forgot, we do have a fourth phase, the aqueous phase. This just means water is also present, and really our compound is dissolved in that water. Okay, why is it not actually written explicitly in the equation? Okay, well, the things written in the equation did something. Okay, and in particular did some chemistry. Water, at least in the general chemistry context, is just being there to help things mix. Okay, we could see the water as a facilitator. And that's such a big word, I'm probably not going to spell that right. Facilitate. A maker of things to happen. Okay. So because of that, it doesn't need to get included in the equation, but we do need to imply its presence so that we know it's there. Okay, so we can show that with our aqueous. Balancing chemical equations. So one of the things that we just kind of went through is that on our sides of our arrow, everything must be consistent. Okay, so that arrow is really our equal symbol. So our reactants can change around to form our products, but all of those pieces must still be there at the end. Okay, because if they're not, something weird happened, and that's not a good thing. I think I got that. Okay, so we have to make sure everything matches. Okay, well, there is no right or wrong way to go through and balance. Okay, but it's usually a good idea to have a methodology associated with it. Okay, so here happens to be mine. Okay, what I would do is write the element underneath the arrow, okay, because that is my equals. That's where everything is supposed to balance across. To the left of that symbol, I will write the number of that atom that appeared. Well, I go over to the left side, and I see one sodium atom. Okay, I know it's 1 because the coefficient in front isn't listed, so it is an implied 1 to begin with. And then I also can check the subscript right after it, and I will have an implied 1 there as well. So 1 times 1, I get 1. So there's 1 sodium atom on the left. On the right, I would do the same thing. The coefficient is an implied 1. My subscript is an implied 1. 1 times 1, I get a 1. The 2's and 3's that we see that come after apply to what's directly in front. So the first 2 goes to the carbon, not to the sodium. The second, or the 3 goes to the hydrogen. Second 2 goes to the oxygen. None of which apply to the sodium. I would then move to the next element, and interestingly enough, I would jump to carbon. Okay? And I want to save hydrogen and oxygen for the very, very end. So I'm going to jump to carbon first. Carbon on the left, that 2 applies to the carbon, so I have a 2. The coefficient in front is an implied 1. That means there are 2 carbons on the left. On the right, I end up with the same thing, 2. And now I have a mild dilemma. Where do I balance next? Okay, hydrogen or oxygen? In this case, I would balance the oxygen first, okay, which might be counter to how I would in other circumstances. And the reason why is that hydrogen shows up in multiple places on both sides of the equation, which makes it more difficult to count. So if I'm lucky and I count my oxygens, 2 and 2, if all other elements are balanced, when I do my final last step of balancing the hydrogen, hopefully everything adds up. So I have 1 hydrogen here, I have 1 hydrogen here, ooh, tricky, I have 3 hydrogens there, and I have a whopping total of 5 hydrogens on the left, and on the right I have 3, and I have 2, 5 hydrogens. This means that my equation is balanced, and I can now go through and answer a variety of questions about it. The most common question is, what is the sum of the coefficients? Okay, well, the coefficient is the number in front of everything. Okay, so what is on the purple line for each of those species? Okay, well, on a multiple choice test, you'll almost always see 0 written as an option, 1, and then for this case, probably 1, 2, 3, and 4. Well, our answer ends up being 4, because there's a 1 in front of the first one, a 1 in front of the next one, a 1, and a 1. So the sum of the coefficients, 1 plus 1 plus 1 plus 1, gets us our 4. Okay? We did that really, really fast and without a real set of rules, breaking that down and slowly going cranking through it. Okay? So what I would encourage you to do is to come up with a rule set that works for you. Okay? These happen to be my guidelines for balancing, okay? And I think they consistently work. It's up to you if you want to use somebody else's rule set, but be consistent, follow whatever you can. Okay? Some of the things to watch out for: you may need to predict products before you start, and that may require classifying the reaction. We haven't looked at predicting or classifying yet, so don't stress on those quite yet. We then also need to balance our formulas first. Okay? This really ties back to predicting products, but it's an important statement to make because most students will skip balancing the formulas. Okay? This is really a statement of saying, know your nomenclature. You have to make sure that the compounds that you are drawing are correct before you try and balance the equation. If they are incorrect, then you're going to have a really bad time balancing the equation. Okay? Once we've got that squared away, we can then balance the equation, starting with any atom other than hydrogen and oxygen as a general rule. We'll place whole numbers in front of formulas to increase the amount of all atoms that follow up to the operation. Okay? We'll always put it in front of the formula. We'll never change the subscripts because the subscripts change the compound. That's our nomenclature. Okay? We'll repeat steps 3 and 4 with a new atom until all atoms have been verified. As a general rule, leave hydrogen and oxygen for the last things to balance. It just kind of becomes tricky to decide which one's which. The next part is one of my favorite parts. You need to check your work. And you will check your work by repeating steps 3 through 5, starting with the very first element and working your way all the way through. Okay? You may have to cycle through step 6, as in repeating steps 3 and 5, again and again and again until it balances. What if you've gone through it and you're still looping? You've looped 6 times and it's still not balancing. You're changing all the numbers. This likely means that you screwed up step 2 or step 1. Erase your work, try again, go all the way back to step 1 and 2, try the whole process again. Okay? Very last thing, verify that you use the smallest whole numbers possible. If you followed the procedure correctly from the get-go, step 7 is kind of unnecessary and you shouldn't have to worry about that, but you do need to make sure that you use your smallest whole numbers when balancing. So let's move to a couple examples here. I'm going to go through and do the first one, hydrogen and oxygen reacting to form water, and then I'll leave you to work through the others, and maybe we'll have like a quiz or something like that in class, or just in the video, who knows. So hydrogen, because hydrogen only shows up once on each side, oxygen shows up once on both sides either, so it doesn't really matter which I balance first in this case. So on the left I have 2 hydrogens, on the right I have 2 hydrogens. Okay, so my hydrogens are balanced. What about my oxygen? Well, on the left I have 2, and on the right I have 1. Okay, so the right isn't balanced. Okay, so this is where we'll kind of discuss some things that students can do, or mistakes that students have made. I have seen students go through and do something like this. Oh, we'll make it H2O2, okay, because now I have 2 oxygens, right, and that's what I needed to do. Well, the problem with that is that I then change the identity of the compound. Instead of it being water, it's now peroxide. Life versus death. Pretty big difference. Do not change the subscript. Okay. The other option that I've seen students go through and do is something like this. Okay. I cannot use a large number in a formula. It's got to be a subscript or a superscript at the very end to represent charge. So that also does not work. Okay. What I will do is place the 2 as a coefficient in front. This 2 applies to everything thereafter. Applies to the hydrogen and to the oxygen. So if I break this down, my subscript is 1 for the oxygen, the coefficient is 2. 2 times 1 gets me the 2 that I need, balanced. Okay. Remember in the protocol that I said that you should recheck your work. Okay, so we would go back through and take a look at our hydrogens. Okay, and this is where people go, oh, I shouldn't have to do that, I did everything right. Well, how many hydrogens? There's 2. How many hydrogens in the product? Well, I still see 2, but I also have the coefficient. Those multiply, and it's not 2, it's 4. This means that I don't have this properly balanced. To fix this, the 2 on the left must become 4. To do that, I need a 2 coefficient in front of the H2. The 2 times the 2 sets me up with my 4, and my equation is now, or my hydrogen is now balanced. I can go back and check my oxygen. The oxygen comes in with a 1 and a 2. That sets me up with 2. That balances. I have a 1 and a 2. That again sets me up with 2. That balances. My equation is now balanced. To answer the sum of the coefficients question, I have 5 for my final answer. Possible multiple choices, 3, 2, and 1 would also show up. Okay. 3 because there's 3 species, 2 because it shows up a couple times, 1 because it shows up a couple times. Okay, so you have to be careful in how you go through and balance to ensure that this actually works. Okay, so take a swing at one of those other 3, and you may very well see a question popping up on that. The next part is classifying your chemical reactions. There are 5 primary categories, and we'll actually be adding a 6th at the end of the slideshow, that you need to be able to recognize. So we've got combination, decomposition, single replacement, double replacement, and neutralization reactions. Okay, we've got example reactions for each of those shown below. So if you see a reaction where you take, I don't know, sodium plus chloride to give you NaCl, which reaction is that? Okay, well, I'm starting with 2 things, so it can't be a decomposition. Okay, 2 things work for single replacement, double replacement, neutralization, and combination. I end with only one thing. Okay, the neutralizations end with 2, can't be neutralization. Double replacement, 2. Single replacement, 2, can't be those. The only one that ends with one thing and starts with two things is the combination reaction. Once you've identified the type of reaction, you could then start to answer questions about it, like maybe you need to predict products or other things along those lines. Okay, so you need to be able to look at these and find patterns within them. Okay? Decomposition, you start with one thing and you go to 2. Single replacement, this is where it gets tricky, is we start with 2 things, but in the process of the reaction, we switch 2 pieces. Notice A and B exchange their locations with respect to C. The double replacement, same idea, except we're starting, instead of with A by itself, A is with something, so it's doing a complete swap. Okay. Yeah, I don't want to draw any analogies there because those could be weird. Okay, neutralizations. You'll notice the neutralizations should look really familiar because we're taking a species and we are exchanging that species with each other to get our product. The neutralization is a double replacement reaction. However, it is more specifically referred to as a neutralization because it typically involves hydrogen and hydroxide in what is known as an acid-base reaction. So again, you need to recognize that pattern. In our combination reactions, we have 3 different types. You're not responsible for predicting products, at least on an exam. In this circumstance, you should be able to predict them just because it's relatively straightforward. So working with our nomenclature, we have magnesium metal, so Mg, because it's a metal, we're looking at the solid, reacts with oxygen gas. Well, oxygen gas is diatomic, so it's O2, and I want to specify that phase, and this is going to go through to produce a compound where I mix magnesium with oxygen. If you think back to the balancing rules, I said step 2 that we needed to balance our formula. Magnesium, you're required to know is a +2. Oxygen, you're required to know is a -2. Okay? One of each is the proper balancing for those 2. I now have the balanced formula for magnesium oxide. Notice I don't know the phase. Okay? I don't expect you to know the phase because you're not expected to be able to predict these. It's being used as an example here. If we went back to our balancing reactions, you should be able to now balance this equation and tell me the sum of the coefficients. We will look at the rest of those combination reactions in class. As for our decompositions, this is a single compound and it's broken down into 2 or more simpler substances. One kind of classic example is taking mercury 2 oxide to produce mercury metal and oxygen gas. So we can take mercury to oxide. Oxide's a -2, mercury's a +2. Okay. This is heated, remember our symbols, delta over the arrow, to produce mercury metal plus oxygen gas, which is diatomic. And we were told that our starting material was a solid, and we have a proper formula or a proper equation. Okay, that again we could now go through and balance. Notice again the patterns. We're starting with 2 species, could be more, okay, or 2 things connected as one species that then break down into 2 separate chunks, as noticed by the plus between them. Single replacement reactions. Okay, this is where our predictions will be needed. Okay, and this is one of the big topics we'll talk about in class. Okay, Iron solid is mixed with aqueous copper 2 sulfate solution. Okay, and I conveniently showed a different equation. So let's go ahead and erase that and just work with the one I described. So we take iron solid. Iron is a symbol Fe. It is a solid, so we'll add the S. Plus copper 2 sulfate. Copper is a symbol Cu. Sulfate is SO4. Since it is copper 2, I know the copper is a plus 2. Sulfate, because I've memorized that by now, is a minus 2. This formula is balanced, so that is correct. AQ, and I did this without enough space, so give me a second here. In our single replacement, we need to exchange ions. Well, iron is a metal, copper is a metal, sulfate is a complex ion. So if we're going to do the single replacement, we need to exchange the most similar things with each other. Okay, so which two are the most similar? Well, the metals are the most similar, so we're going to exchange their locations. The copper is going to come out all by itself. The iron is then going to go in with the sulfate, and we would end up with FeSO4. Okay, a couple interesting observations out of this. Number one, I don't expect you to predict phases yet. Okay. Number two, this is actually an equation that you can't predict properly. We have to make some assumptions. So what are those assumptions? Name that product for me. Okay, well, we know we have iron. We know we have sulfate. What was the charge on the iron? Well, I know what the charge on it is now because it had to balance the sulfate. Okay, but how did I know what the charge on the iron was going to be? Because it didn't start as an ion. Okay, it's a good question. I don't know. This is something that would have to explicitly be told to you, or you are required to know it. You're not required to know this one, so we'll just make the assumption that iron became a plus 2. The other thing to notice is what happened to the copper. It started as a plus 2 to balance out the sulfate as a minus 2. And yet when I drew the copper as a product, I did not specify the charge in the upper right-hand corner. Or rather, I did. There isn't a charge. So in the course of this reaction, iron with no charge becomes iron with a plus 2 charge. Copper with a plus 2 charge becomes copper with no charge. This is an important observation for your single replacement reactions, and it's going to snowball into our discussion on redox reactions, which is a whole nother can of worms. Okay, so we've got a bunch of examples here and this weird activity series, which we'll talk about in class. Take a swing at balancing one of those equations, or perhaps maybe you should take a swing at balancing this reaction. When it comes to predicting, again, we'll talk about it in class and realize, as it's shown in the upper right-hand corner there, I will give you a modified activity series because you need it to be able to answer these kinds of questions. Double replacement reactions, similar to the single replacement in that we exchange an ion, but now we're exchanging 2 ions. So if we take a look at our first example, we have barium chloride. So barium begins with Ba, chloride is Cl. Okay, it's aqueous. It says reacts with, so we put a plus sign, aqueous potassium chromate. So potassium is a K, chromate is CrO4. Okay, and I would want to go through and do my reaction, because I said this was aqueous. I would want to take this to my products and I would just exchange. For those of you screaming at me, hold your breath, we'll come back to you in a second. We've got metal and metal. We'll exchange those metals for each other and we would end up with potassium chloride and barium chromate. Okay, and we would then potentially end up with our answer. Okay, and believe it or not, we would be wrong. Okay, so now the question becomes, why were we wrong? Well, remember back when I said we had to deal with balancing appropriately? We have to make sure that we've balanced our formulas. Barium is a +2, chloride is a -1. That formula is not correct as written. It needs to have 2 chlorides to balance the barium. I need to have that 2 there. When we move to the next one, potassium is a +1, chromate is a -2. Again, not balanced. I need 2 potassiums to balance the chromate. Okay, that information is embedded in the nomenclature, which you are responsible for, so you have to check it. If we look at our product, we have potassium +1 and chloride -1. We might say that's balanced. One thing to kind of be aware of, a lot of students will take this 2 and bring it over. Okay? We have to understand the meaning of that 2. Okay? Because you're not allowed to bring that over. That 2 is present to balance, or balance, like blave, balance the chromate. If I brought the 2 over, I need to balance with chromate. Well, is potassium with chromate anymore? No, it's with chloride. So that 2 does not belong with the potassium in the product because there's no chromate. If we go through and do the same thing with the chloride's 2 is present because it needs to balance the barium. If we look at the product, the chloride is not next to barium, it's next to potassium. I don't want to bring that 2 across. If we go through and look at the barium chromate, it's +2, -2. That formula was balanced outright. Okay? We could theoretically then go through and balance this equation and tell me the sum of the coefficients. Continuing, if you want to give it a shot, try and balance that next reaction. Okay, but more importantly, what we're going to pop up with is our answers. Okay, without balancing. How did we know it was solid versus aqueous? Because in the double replacement reaction, not only are you required to do your exchange to predict your products, but you also must predict the phase. That's an extra little trick. To do that, we have to know more information. We have to have what's known as solubility rules. So we will apply those solubility rules to the 4 products shown below. Barium chromate. So what I want to do is find either barium or chromate in the table above. Chromate shows up as rule number 7. Barium doesn't explore. Barium shows up here with hydroxide. Okay, and that is it. Okay. Oh, there it is. Okay, so we've got barium now covered. So barium with sulfate, it's not with sulfate, so rule 5 is irrelevant. Barium with hydroxide, not with hydroxide, so rule 10 is irrelevant. I'm looking at rule 7. Rule 7 falls under the ionic compounds containing the following ions are generally insoluble. Insoluble means they did not dissolve, which means they were solids. So ionic compounds containing these ions are solids unless, okay, so chromate is a solid unless rule 1 gets in the way. What was rule 1? Rule 1 says alkali metals. Barium is not an alkali metal, so the phase must be a solid. Okay, so let's try it again with, say, potassium chloride. We see potassium showing up right away. I see a chloride. I don't think we really care about any of the others, so there's the 2 locations that pop up. Okay, potassium showed up first, so it's in reference to the header above it. It says generally soluble. Soluble means it dissolves, which means the phase should be aqueous. Okay, so alkali metals are aqueous unless of an exception. So when we read Rule 1, do we see anywhere that it mentions anything about exceptions? Nope. So there are no exceptions. It's aqueous. We don't even have to look for the chloride. But let's, just for giggles, take a look at the chloride, because I know you guys think that's fun. So let's go ahead and take a look at the chloride rule. Chloride, we're generally soluble. Oh shoot, but there are exceptions to that. Okay, the exceptions are solids, as insoluble if it's lead. Potassium's not lead. If it's mercury, potassium's not mercury. Or if it's silver, potassium's not silver, must be aqueous. Okay, so take a minute and take a look at the next two compounds and prove to yourself by identifying which of the rules applies to their solubilities. Neutralization reactions are the same thing as a double replacement, except now we're just bringing in acids and bases into this. So if we look at the complete neutralization of sulfuric acid with potassium hydroxide, we go back to our nomenclature. Sulfuric acid, because there's no hydro, it's ternary. Because it's sulfuric acid, we know there's hydrogen. We know it's sulfate because it's ic. Sulfate is a -2, hydrogen's a +1. I need 2 hydrogens to balance this. Because it's an acid, I know the phase is AQ. Plus potassium hydroxide. Potassium's a K. Hydroxide is OH. Potassium is a +1. OH is a -1. I didn't specify the phase. So 2 answers for coming up with the phase. Number 1, take a look at solubility rules. Number 2, be a jerk and leave it blank. Okay, because you don't have the context to be able to apply it. I will argue you do, because you're supposed to know the solubility rules, just so you know. To do our reaction, we now need to predict our products. What happens? The hydrogen needs to exchange with the potassium, so I would end up with potassium next to the sulfate, and I would end up with hydrogen next to the OH. Notice in that exchange, I did not take the subscript, okay, for the hydrogen. Why is there a 2 there? To balance sulfate. It is not with sulfate in the product, which means I do not take the subscript. It stays as just a 1. I have to decide what that is by balancing that formula. Potassium is a +1, sulfate's a -2. That doesn't balance. I need the 2. Hydrogen's a +1, hydroxide's a -1. That is now balanced. To specify phases, I should be able to determine the phase of potassium sulfate as being aqueous using solubility rules. HOH is a liquid, and we have my full equation. Okay, is this equation balanced? Nope. That might be a good question to ask. The last reaction type that you will see potentially show up would be a combustion reaction. This is the reaction of some organic material, this is at least carbon and hydrogen, with oxygen gas. The fun thing with our combustion reactions is they will always produce carbon dioxide and water. Okay, and actually give me a sec here. Oh cool, I have an example here, I don't even have to come up with one. We have carbon and hydrogen reacting with oxygen gas to produce carbon dioxide and our water. Okay, and then we could go through and try and balance the whole equation. You should be able to go through and do that. Do I have a second example? Oop, I don't. So that might very well be it. So on that note, we'll almost end the video. We'll have one last quiz question here on the sum of the coefficients for this balanced equation. Yes, it is a beast, see what you can come up with. We'll discuss it in class. Thanks for watching. Enjoy the rest of your day.